Thanks. Okay, hello everyone. Today we are going to talk about bio-inspired front-end engineering. So I'm Kylie. I've been doing front-end engineering for more than half a decade. So this is the link to my GitHub profile. You can follow this link. Actually, I've been trying to get into the Twitter thing, but I wasn't very too successful. So if you are interested to follow me on Twitter, you can use the same handle. It's the same, but I'm not going to include it here just in case you are interested. So I'm currently working as a staff engineer at KKBOX HQ in Taiwan and doing all sorts of front-end and JavaScript stuff. Now, I'm not sure if this is also commonplace for everyone's home country, but here in Taiwan, a good portion of front-end engineers in the industry aren't coming from a computer science background, so including me. So just being curious while we're at it. So how many of you aren't coming from a traditional computer science background? Please raise your hand. Please just being curious. It's like a dozen or more people. Okay, so it's not a lot of people. So maybe I'm not a common people. I don't know. So, okay. Well, just like I've said before, I'm not coming from a computer science background. My academic background is actually having nothing to do with computer science at all. So, actually, I used to be a telescope operator on Mauna Loa in the Big Island of Hawaii. So it's not a very big telescope. It's a radio telescope. And we are trying to observe some critic properties of the microwave background radiation. So it's not very interesting, but I have a long-standing passion for astronomy since my youth. Actually, during my school years, my academic years, I'm studying chemistry and biology, molecular biology, cellular biology, and so on. So I would not say they are interesting, but they can be enchanting at times. So you may be wondering that astronomy, chemistry, biology, these things sound totally different. Okay, and you may think they are unrelated to each other. But actually, I'm trying to let you know that all of them are like beacons of light pointing to some of the archaic, the most ancient and most profound questions for us human beings since the dawn of civilizations. So you may not know this yet, but they also have some striking resemblances in places that you may have yet to discover. So maybe you will think that this claim is very dubious, unbelievable, but after all, you will see, because while you may think that the differences is astronomical versus atomical, how can they be, how can they share any resemblances? How could it be? Well, it's not only orders of magnitude apart. We are basically talking about two very different ends on the scale of our universe, right? So how could there be any kind of resemblances, So let's take a look at this picture, this background picture. What does it look like to you? Does it look like a group of cultured cells on the petri dish? Or maybe it's like a representation of our neural network in our brain? Now the real answer is, this is a computer simulation of the based on real observational data, that's the very large structure of our universe. It's the largest known structure in our universe. We are calling it like a filament of our universe. So as you can see, our galaxies, they scatter. They doesn't really scatter around the universe. They sit on certain filaments along a straight line, and there's nothing in between. It's just void, nothing else. So the similarities in the visuals not mere coincidence. Actually, scientists are saying that there may be some system dynamics that we haven't yet fully understand, having been in play here, and this may be a more in-depth research into this area may show us some unknown science. So let's take a look at another example. So here's something. Yeah, it looks like an embryo, in very early stage embryo. Now, we actually have a specialized term for this in biology. It's called a morula. So a morula is a fertilized egg undergoing a few splits, like from a single cell to like 16 or 32 cells. This is a very early stage of a single life. It's only a few days after fertilization. So it looks like, because it looks like a mulberry, so it's called a morula. Okay, it's a Latin phrase. Now, apparently this is not a fertilized egg. This is not a morula. So I'm not. Otherwise, I won't be showing it here. So it's actually a planetary nebula called Eskimo Nebula. It's a few thousand light years away from the Earth. So ironically, this planetary nebula, or should I say every planetary nebula, is formed at the end stage of a dying star. So it's totally contrary to the early stage embryo. Well, so when a red giant reaches the end of its lifespan, it will kind of like just explode. Well, actually, it's not explosion, but it actually kind of pushing the outer shell of itself into the interstellar space. And these materials will get ionized. And they will form the nebula you see here. And the inner core will like condense into a white dwarf. And the white dwarf will be left alone in the space and undergoing an eternity of thermodynamic death. So this can be sad, but this is the very real fate of the central star of this planetary nebula, and this will also be the fate of our very own sun. So this is not fiction. This is going to happen in some distant future. So maybe you think this is a sad thing, but I'm going to tell you that this is not necessarily a bad thing, because if not of these dying stars, we won't be here today. Life on Earth will never happen at all, because the planetary nebula and the explosion of stars is very crucial to the generation of life. So be it a tiny embryo or a dying red star, they both play an inseparable part in the birth of life. So that's because we're all star children. So more than 90% of our body's mass were forged by some long-gone star in the distant past. Some gigantic star, that is. So, for example, if you are like 70 kilograms, 63 kilograms of your body mass is made from atoms forged in some distant past inside the core of a star, a giant star. So, well, that's because, in the beginning is the Big Bang, that is, and there is only hydrogen and helium. So every heavier element, like lithium or carbon, are formed in a later date during a process we call nucleosynthesis, which is basically nuclear fusion inside stars. So elements that are substantial to organic life forms like carbon, nitrogen, oxygen, they won't be here today if it's not because of this process. So now that you can see that, well, astronomy and chemistry and biology, they are not that different. Or should I say, they both of them point to some, single greatest mystery of all time, the origin of life. So they will give answers to questions like how are we here, and why we are here, and what the heck, this is JSConf, damn it. This is not like a philosophy conf, So why are you talking about this? Where's my refund? Damn it, I'm going out. I'm getting out. No, please don't do this, okay? Or, Thomas will be mad at me. So what I would like to really talk about is that why we are here today to listen to this talk. So I'm hoping that we can agree on these three things, which is convey ideas and thinking process, trying to exchange ideas and see how ideas flow, and to let you know that maybe we should value cross-disciplinary knowledge and how to draw inspirations from the nature, the universe. And we will use a classical example, which is a class composition as an example for during our talk. So first, just making sure that everyone is on the same page. We're talking about ES6 classes very quickly. So this is how ES6 class works. I'm sure that most of you should know this, but just in case you haven't seen this before, this is how it works, and it can be translated to ES5 in roughly like this. And as you can see, this is a well-known pattern for classical JavaScript development. So it's nothing special here. And there's also subclassing in ES6, which goes like this. You can extend from a base class, and you can use supercalls. So it can be translated down to ES5 like this. It's a little bit more complex, but it's nothing really hard. Basically, it's just telling you that how actually you are extending from the prototype chain and how you are doing this supercode. So nothing special here as well. So maybe more interesting is another proposal for ES7, which is the class property declarations. It's actually still in a very early stage. It's still in stage 1, but you can use it today. And it looks like this. Previously, you have to attach some properties in the constructors, but if you are using this new proposal, you can attach the property of class like this in design time. Makes it feels like a more integral part of the class. So you can do all this stuff if you are using Lebel already. But just in case you don't know about this, you can go to the Lebel website and grab the executable and try experimenting some of this new syntax. And there is also a repo, online repo you can get to play about. So let's go through some quick facts. So first, ES6 classes are designed to be maximally minimal. So what does this mean? Maximally minimal is so strange, Well, actually, it means that the community spend a lot of time trying to make sure that they put the tiniest bit of things into the new specification while enabling it to do a lot, the maximally possible things. Yeah. So that's why they only settled on some very basic features like extend and supercalls. So there's nothing like mixins and traits and so on. So just make sure that you know this. ES6 classes is not actually a classical inheritance. It's still prototypal. And it's just trying to formalize on a very specific pattern of the prototypal inheritance, which is the constructor pattern, because everyone seems to be using it. So it's not actually it's actually trying to unburden the function keyword, because before the ES6 era, function keywords, being used in so many places, like declaring a method, a constructor, a callback, whatever, and you are seeing this keyword everywhere. So this is actually a good thing for static analysis and readability, because it makes it more clear that what you are trying to do with this block of code and convey your intent more clearly. So in my humble opinion, ES6 classes appear at exactly where the next level of language abstraction would appear, and it's just here for our usage. But there are a lot of naysayers during the formalization process, and even now, there are a lot of people who are opposed to this new feature. But my take is this: technology by itself has no good or evil, and the same should apply to technique. So what really matters is the intent of doing things, and why are you doing this? It's not actually the technology or the technique itself. So there are some high-profile figures being very vocal about the inclusion of classes in ES6, but I think the inclusion itself is neutral. It's what you are trying to use it on that matters. So one of the biggest reasons people are opposing, classical inheritance or inheritance itself is because of the fragile base class problem, which means that something bad will happen if the inheritance chain gets too long. Like, for example, you can see this in a lot of places. Like, for example, in CSS, basically CSS itself is a giant inheriting style sheets. It's code cascading style sheets after all. So, each style applies to its cascading down, the style rule chain, and basically the whole design of CSS was encouraging the use of globals. So this is a bad thing for developers, and developers have been struggling with this for so long. And there's also the extend in SAS, while extend is very powerful, it can cause some troubles for if you are using it in a wrong pattern or just using it in a wrong time. So there are actually a lot of online tutorials trying to tell people when should you and when shouldn't you use extending sauce. And this is weird by itself, because if something is good, you shouldn't have to worry about this. It should be not very prone to error. And another thing is the scope chain in AngularJS. It's basically a very long prototypal inheritance chain down each scope. So it's also been very prone to error, and a lot of people have been complaining to this, but I'm not sure if there is any good solution to this problem. Maybe there is one. I'm not sure if this is in AngularJS, but overall you should do composition over inheritance if the situation allows, because long and shaky inheritance chain is very bad, and it's not very easy to handle with. So, if you've been here yesterday, maybe you've heard the wonderful talk about CSS modules and so on, the ICSS format. If you've been here yesterday, then you should know about this newest solution, newest state of the art in the front-end development area. We can use CSS modules to modularize the CSS we're using and avoid the global style sheet problem, and maybe you should stop using cascading after all, at all. Don't use it. And system modules also provide some capabilities over class composition, and itself can nullify the problem of source extent. And for AngularJS, maybe you should check out React for a healthy work, maybe, because React props is doing this in a very different fashion than the scope chain of AngularJS. So by design, it avoids the problem at all. So just in case you haven't checked out React already, you can go figure it out on their website. They have a very extensive documentation. And here's a little bit about React mixins. Basically, there was a mixin implementation in React prior to version 0.13. When you're using the old React create class method, you can do it like this. But after a new update several months before, they stripped it away. So if you are trying to use ES6 with React, there's nothing you can do now, to include the mixins, which is, it's kind of sad, because pure random mixins, if you are using React, you should know that this is very essential part of React, because it helps a lot to reduce the performance, to improve the performance of the page. So there was a debate all over the internet about trying to bring mixins back to ES6 React components, but my take is that this is a bad idea because mixins and traits have their own problems. Their main problem is that they are too weird for daily uses, because both mixins and traits trying to address a problem, which is when the method overlaps, they're trying to resolve the method, either implicitly or explicitly. Like, for example, mixins is doing this implicitly. So, for example, like in Ruby, if my memory serves me correct, in Ruby, it will try to resolve your mixins in a write first, depth first order. And in Python, there is another very delicate algorithm called C3 linearization that's trying to do all the things for you. But the problem is it's too implicit, and you don't know what's happening behind the scene. So there's another composition method, which is traits. It's trying to do this explicitly. So you have to declare on each method what you are trying to do with this method when there is a conflict. So there are a few options like symmetric sum, which is addition, and removal or renaming, but it's getting too excessive for your daily usage. You're not going to want to do this for all your methods. If you are maintaining a large scale project, this is going to be a lot of work, and the chances you are using this is nearly zero. So maybe not using this approach. So that's where I start to explore some alternative methods for composition, which led me to the following inspiration. So I start trying to look for some naturally occurring structures, and it turns out that cells, the basic component for life, is a very good example for this case. And we're going to go through this very quickly, I hope, because this is not maybe not very interesting to some of you, but we have to learn some basics about cells. It is one of the most interesting and miraculous structures of our universe, because there's nothing like life. And it has withstood eons of revolution to come to this current state, and it's the so far the only known fundamental and universal building block of life. So what's the secret? Maybe we should do it from the very beginning of life. Let's talk about how life begins. So actually, there's no definitive answers yet to this problem, but the most convincing, theory right now is a biogenesis, which means that life basically happens at a very deep seafloor, and there are a lot of hydrodynamic vents, spewing hot springs from the core of the Earth, and life forms there because it provides heat and the necessary chemicals for reactions to begin kicking off some biochemistry process. And it also provides some necessary environment to form the membrane of the cell. So we have mentioned that the formation of the membrane of the cell is very important because without a compartment, you can call it a cell. So this is the first thing we are going to look at. I've been trying to avoid this kind of diagrams, but this is unfortunate. We have to face it. We have to face it some moment during this talk. I don't want this sound like some bullshit from the textbook, but yeah, let's face it. So this is a protocell, but actually it is not a cell. It's just a ball being formed by a not so thick oil layer. So all these small molecules here each are a oil molecule, and a very good way of thinking what it is that you can think of it as an object, and naturally occurring object. And it's an empty object. It's not something. It's just an empty object. So while some people are not very acceptable to the idea that life kind of cell-originated, but think about this. It takes the Earth 1 billion years to build an empty object. So that's not very smart, right? So if you come to think about this, it's not very surprising. So some more millions of years later, there are some more advanced, not so advanced, but more advanced than a protocell cells called prokaryotic cell, which is basically bacteria. Okay. So as you can see in this diagram, inside a prokaryotic cell, there is basically no structure at all. So a very good way of thinking about this is that, think about POJO, plain old JavaScript object, or plain old JavaScript, just plain old JavaScript object. So how do we use a plain old JavaScript object? There's basically no structure. You just open a lot of properties and throw integers and strings and methods and booleans and all kinds of things inside. And this is what you are seeing here. There's no compartments. DNA and RNA and all kind of stuff are mixing together inside the compartment. So it's actually not a bad design. I'm not sure. I'm not here to judge, but it gets things down. So come to think about this, the heaviest biomass on Earth is formed by plankton, which is prokaryotic. Prokaryotic life form, but they can form something too advanced because this kind of structures can only go so far, but they are still nonetheless very efficient. They can get things down, but yeah, it's just go so far. So after some more millions of years, after some interesting process, a more advanced variant of cells emerged, which is called a eukaryotic cell, which is what we are formed. Everyone here, your body is formed by a lot of prokaryotic cells, which is so far the most advanced kind of cell. They are advanced because they have a lot of, compartments, compartments, encapsulation, structure, all of these are good things. So just look at it, this is some kind of good stuff. It's like a React component instance with a lot of live method hooks for your usage. So another interesting thing to think about is that, there's a not so small gap between a prokaryotic cell and a eukaryotic cell. There's so much more structure, so much more compartments. Actually, they have a specific name called organelle. Organelle is like literally a small organ. So there are a lot of organelles here, and how did they come into existence? This is another unanswered questions in contemporary science, but there are some very convincing theories right now that tries to address these problems. One of which is called a symbiogenesis process, which basically means that our primitive cell ancestors try to eat some other cells, and they found out that instead of eating them, feasting on them, they can try to coexist with them. So one of the examples is the cytoplast, which is what you will find in all of the plant cells. Cytoplast itself is believed to came from symbiogenesis. So their ancestor is very likely some germ, some cyanobacterium, and in some ancient past, some cells try to eat this kind of small cells, and after they eat them, they found out that instead of shred them and feast on their substances, it's much more better to let them stay there and that they do their things, because it's actually they are basically some sugar generating factory. So free sugar, why not? So so they just stayed and co-evolved with some primitive cells. And this also happens for another organelle, another cell organ called mitochondria. So the order is actually first there is mitochondria coexisting with primitive cells, then chloroplast. So a lot of this process happened in ancient times that we are not yet very sure if they happened or not, but we believe that it's one of the very possible hypotheses about the origination of advanced cells. So now that we have come to know about this, how about that learn from the nature and try to implement this kind of structure in our code? So bio-inspired class composition. So let's tweak our earlier implementation a little bit. We are not going to declare a organism. We are going to define a cell instead. So here are a few properties for a cell: age, the amount of glucose molecule, and there are actually energy molecules, but I'm not going to explain here. I'm going just to represent them in some rough integer. And there's also a very basic method called grow. Okay, so very basic, and grow basically consumes energy and grow the cell and increase its age. And here are how we would like to define our mitochondrion and chloroplast, because basically, in essence, they are still cells. They still preserve a lot of traits about cells. They have their own DNA. They have their own RNA synthetic process, and a lot of similarities with a normal cell. So we're just extend them as a base class of using the cell as a base class. And mitochondria is actually like a power plant for our cells. So it creates energy. It consumes glucose and turns them into some energy molecules. The ratio is not actually 1:1, but I'm trying to keep things simple here. So there's also chloroplast. Chloroplast is do simple things that they use the energy from photon, the light, and some more carbon dioxide, and transform, somehow generate glucose and oxygen. Now this can be a little bit daunting, but I'm just going to let you skim past this really quickly. But if you are interested, we have a link to the code later. So basically, I'm defining some more methods for a plant cell. It can basically the main thing is that it can do something like divide an existing mitochondrion to make it into two. And there's also some way to channel energy and glucose molecules within the cell and its organelle, like between cytoplast and mitochondrion. And this is how we use it. So, just the same, we knew a plant cell, then we can invoke the methods attached onto it. And if you are interested, here's the result and a link for you to play. It links to a Lebel repo page, which you can try to play around and see if you can find something more interesting. Now this is more like a proof of concept. So if you are trying to do something, you can add more abstractions into it. I didn't add too much abstractions because I'm just trying to get the points across, but there's so much potential to this new way of class composition. But actually, I'm trying to tell this. I'm letting you know that I'm being honest here. I seriously doubt that this is the first time someone using this technique because this is actually not a very hard technique. So, for example, if you are trying to explain this to a 5-year-old, you can just say something like, "Oh, I'm, instantiating some objects in the constructor method." That's basically it. But the point is, what matters here is that why you are doing this, the reasoning behind, and the different thinking process will yield different results in a subtle way. For example, flux, Facebook flux, if you have checked into the structure of flux structure in depth, you will know that this is basically a mediated pattern in disguise, but there are some subtle differences or details in the flux structure to make it shine through other similar implementations. So what's more important is why you're doing this and the idea, your thinking process behind. And perhaps now you will come a little bit closer to my ideas that cross-disciplinary knowledge is somehow useful, and you can draw inspiration from the nature because it's like a giant simulation playground, and the nature is doing all the hard working for you and coming out some of the best way of doing things. So look around the nature, and also it's not necessarily a bad thing to do the same thing that other people have done before, because for example the eye, the window of our soul, has been evolved for like 50 to 100 times independently. It's not a single shot. It has do a lot of evolution on its own independently. So there are actually a lot of kind of eyes existing on this earth. There are some sea animals that can see like a lot more colors than humans can do. So it's not necessarily a bad thing. So so how about we, pay some more attention to our environment, and maybe there are some inspirations waiting to be drawn. Okay. Now, thanks for thanks for watching. And
thank you, Kai.
Yeah.
Thank you.